Every massive, isolated cosmic body under the action of gravity takes a shape close to a sphere. The brilliant scientist Eratosthenes first determined the exact dimensions of our planet using the proven method of arc measurements. Direct measurement of a vast distance between remote points is impossible due to the presence of various natural obstacles. The efficient method of triangulation allows accurately calculating the arc length by measuring the angles of a geometric network.
You know, for thousands of years, one of the biggest questions humanity faced was, believe it or not, deceptively simple. Just how big is our planet? Today, we're going to dive into the incredible ingenuity it took to answer that question, a real journey into the science of geodesy. So first things first, we have to start with a core principle. The law of universal gravitation tells us that any really massive spinning body out in space will, over time, be pulled by its own gravity into the most stable shape there is, a sphere. It's why planets are round, and as we can all see from those amazing pictures from space, our Earth is absolutely no exception. All right, so here's our roadmap for this explainer. We're going to start with the basic idea, then we'll look at a truly elegant solution from the ancient world, understand the real-world problems that it ran into, and then we'll get into the incredible technique that finally cracked the code. Once you accept that the Earth is a sphere, you're immediately faced with a pretty monumental question, one that scientists wrestled with for centuries. How in the world do you measure the size of a planet that you're standing on?
I mean, it's not like you can just roll out a cosmic-sized tape measure, right? That's just impossible. So the solution can't be a physical one. It has to be an intellectual one. It's all about using the geometry that's built right into the shape of the sphere itself.
And you know, the theoretical key to this whole puzzle was figured out a long time ago. We're talking about a Greek scholar named Eratosthenes, who came up with a method of stunning simplicity and power way back in the 3rd century BC. Okay, so picture a slice of the Earth, a simple cross-section. We pick 2 points, let's call them O1 and O2, that are on the exact same line of longitude, the same meridian. The actual physical distance between them on the ground, which we'll call L, is just a little piece, an arc, of the Earth's total circumference. Eratosthenes realized that if you could just figure out 2 things, that ground distance L and the angle separating the 2 points, which we'll call n degrees, you could plug them into this exact formula and calculate the planet's radius, r. It's pure, beautiful geometry. And getting that angle, n degrees, well, for an astronomer, that's pretty standard stuff. It's just the difference in latitude between your 2 points. You can figure that out by measuring the height of the sun in the sky at both locations. So in theory, it's perfect. All you need are 2 numbers, a distance on the ground and an angle in the sky. But, and this is a huge but, the mathematical elegance of this idea smacks right into a very big, very real-world problem. Measuring the angle is one thing, but measuring that linear distance L on the ground, that's a whole other ballgame. Seriously, think about it. How are you supposed to measure a perfectly straight line between 2 spots hundreds of kilometers apart, when the surface of the Earth is covered in obstacles and, of course, it's curved? Trying to measure that distance directly with, say, chains or measuring rods is just a non-starter. You've got mountains, dense forests, huge rivers, deep valleys. The real world gets in the way. So the solution to measuring this seemingly unmeasurable distance is a truly powerful geodetic method. It's called triangulation, and it is an absolute triumph of measuring something indirectly. Here's the core idea, and it's brilliant. Instead of even trying to measure that one long, messy line, you build a chain of interconnected triangles right alongside it. This whole network of triangles connects your start point, O1, all the way to your end point, O2, using a bunch of intermediate points. And at each corner, each vertex of these triangles, they would build what's called a geodetic signal, basically a tower or a big wooden pyramid. They'd put them up on high ground, maybe 30 or 40 kilometers apart, so you could get a clear line of sight to at least 2 other towers. It also gave them a stable spot for their instruments. Now, the process itself is incredibly meticulous. Everything, and I mean everything, builds upon one single hyper-accurate initial measurement. The strength of the entire chain of triangles really depends on the precision of that very first link. So, the method has 4 clear steps. First, you measure one side of one of the triangles, called the basis, with the absolute highest precision possible. Second, surveyors go out and measure every single interior angle of every triangle in the whole chain. Third, using those angles and that one known length, you use trigonometry to calculate the length of every other side. And finally, you mathematically project that whole chain onto the meridian to find the distance L you were looking for all along. And when I say highest precision possible for that first step, I am not kidding. Modern techniques let us measure a 10-kilometer basis with an accuracy of plus or minus 2 millimeters. That is just an astonishing feat of engineering. So, once that basis is locked in, the only other physical measurements you need to make are angles. And those are determined using incredibly precise instruments like theodolites, which are designed to measure horizontal and vertical angles with extreme accuracy.
So, just to recap the whole process, you start with one single, known length and a whole series of known angles. From just that information, the lengths of all the other sides in the network can be calculated, one after the other. That information just propagates down the entire chain and eventually gives you the exact distance you were trying to find in the first place.
But hold on, there is one last, absolutely crucial refinement we need to talk about. See, you can't just use the simple flat geometry we all learned in high school because our triangles aren't on a flat surface at all.
The calculations have to be a lot more rigorous. They have to account for the fact that these are not plane triangles, they're actually spherical triangles, laid out on the curved surface of the Earth. And that means the sum of their angles is not 180 degrees. This is where spherical trigonometry comes into play.
And this leads to a final, really fascinating idea. To measure the size of a sphere, we end up using a method based on triangles. But the math for those triangles has to be corrected for the very curvature we're trying to measure in the first place. It's this beautiful, self-referential puzzle that sits at the very foundation of knowing our place in the cosmos.
Thank you, friends. Strive for understanding and become wiser. See you soon.